Welcome back to this lecture on algorithms. In this last segment, we will talk about the change-making problem, which is very different from the search problem and the sorting problem we talked about so far. Here is a description of the problem. You're given an amount n of cents, say, and a set of coins you're allowed to use. For example, quarters, nickels, dimes, and pennies. And the question is, finding the minimum number of coins that add up to the amount n. So the answer to this problem will be a procedure, that is, an algorithm that does not return anything. Instead, we're just going to print the coins that make up the amount n on the screen when we run it. The name of the algorithm is make change, and the two inputs are, one is the set of the coin denominations, you have k of them, and a single integer, which is the amount you need to make change for. Now, instead of describing the algorithm in detail, I'm just going to list it here in full, and then we're going to use the following theorem to demonstrate how it works through a trace. So the first theorem in this lecture states the following. This algorithm finds the minimum number of coins to make change for 43 cents when the denominations are 25 cents, 10 cents, 5 cents, and 1 cent. So, to prove this theorem, we're simply going to trace it using the inputs stated in the theorem. Now, the first step in the algorithm is to sort the elements of the set. Remember, a set is not sorted, but we're going to convert this set into a ordered sequence using one of the sorting algorithms that we talked about earlier. So as a result of the sorting, we get the coin denominations sorted from 1 up to 25 and indexed from 0 to 3. In other words, k is equal to 4. We have 4 different coin denominations. Now, we can start the for loop with I is equal to k minus 1. That is, we're going to start with k equals 3, so we're going to consider quarters first. Now, is the amount we need to make change for, 43, greater than 25? The answer is yes, so we can put a first coin on the change pile, which started empty. So we put down in red here a quarter, and now we only have to account for 43 minus 25 cents. So we change the value of n to reflect the fact that we already put a quarter down, and n goes down to 18. And then we go back to the top of the while loop and ask, is 18 greater than or equal to 25? The answer is no, therefore we can't use any more quarters. We're done with the while loop, and we can start the second iteration of the for loop, which takes I to the next value down, namely 2, so now we're going to consider dimes. So for I equals 2, we ask ourselves, is the current value of n, namely 18, greater than the value of a dime? The answer is yes, therefore we can put a second coin on the pile, namely a dime, and therefore we can reduce n by 10 to get 8. We go back to the top of the while loop and ask if 8 is greater than or equal to 10. The answer is no. That is the end of the while loop, and we're ready to start the third iteration of the for loop. I is equal to 1. That is, now we're going to consider the next coin denomination down, namely the nickel. Is n, that is 8, greater than or equal to the value of a nickel? The answer is yes, therefore we can add a nickel to the change pile. We can reduce n by 5 to get 3, and we go back to the top of the while loop and ask, is 3 greater than or equal to 5? And the answer is no, so we can't use any more nickels. We're done with the while loop, and we're ready to start the next iteration of the for loop. The next iteration of the for loop corresponds to the value of I equals 0. Notice this will be the last iteration of the for loop, That's because we're now considering the last coin denomination we haven't looked at yet, namely the pennies. This iteration will be a little bit more interesting. So at the top of the while loop, we ask if n, that is 3, is greater than or equal to 1. The answer is yes, so we can put a penny on the change pile, and we reduce n from 3 to 2, since we just accounted for 1 more cent, and we ask if 2 greater than or equal to 1, and the answer this time is yes. In other words, we can put another penny on the change pile, so we do that right away. That's this line, and then we decrement n by 1 again. So n is equal to 1. Go back to the top of the while loop. Is 1 greater than or equal to 1? And the answer is yes. So we put a third penny on the change pile. We decrement n by 1 to get n equals 0. And we ask at the top of the while loop, is 0 greater than or equal to 1? The answer is no. And this is the end of this while loop, which is also the end of the algorithm since we're done with the for loop. So in conclusion, this algorithm made change for 43 cents by making a change pile containing a quarter, a dime, a nickel, and 3 pennies, which indeed add up to 43 cents. And if you look at it on your own, convince yourself that this is the smallest possible number of coins you could have made change for 43 cents. In other words, with this reasoning that you need to do on your own, we have proved the theorem number 1. So this algorithm is actually an example of a well-known class of algorithms in computer science called greedy algorithms. This algorithm is called greedy because at every step in the algorithm, what it does is it tries to use the largest coin denomination available first before it tries the smaller denomination. So notice we tried the quarters first, which is the biggest denomination, then the dimes, then the nickels, then the pennies. And the reason for that is the hope that if you use the bigger coins first, then at the end you will have used the minimum number of coins. So this strategy is called greedy because, again, at every step you greedily try to make as much change as possible to minimize the number of coins. Now what I would like you to do is to practice tracing these algorithms on inputs of your own choice so that you can convince yourself that this greedy algorithm indeed works. Okay, so if you worked hard enough on tracing this algorithm, you should have noticed that actually it does not work in all cases. And that is the statement of the following theorem. Now remember that the definition of an algorithm is that, or one property of an algorithm is that it produces a correct answer for every possible problem instance. Well, the reason this pseudocode given above is not an algorithm for that problem is because it actually does not give the correct answer for every possible set of inputs. So what I want you to do now, if you haven't found it yet, is to find one example of 2 inputs for which this algorithm does not return the minimum number of coins to make change for the particular value of n that you choose. And by the way, you're not limited to values in the set S that are actual coin denominations. You can use any positive integer that you need to break this quote-unquote algorithm. So, I'm not going to prove this theorem for you. I will let you prove it on your own, again by finding a counterexample. And this concludes our lecture on algorithms.